Hello बच्चों, सत श्री अकाल and namaste from my side. How are you all? So guys, this is Indrajit Singh welcoming you all onto the most sensible platform, right, for an aspirants, those who are preparing for JEE NEET kind of examination. So guys, how are you all? Right. Okay. So guys, we started with the units and measurement. Now we are on to the solids and fluids. Right, it has been divided into the two parts. The mechanical properties is divided into the two parts. The first one, it is in solid, right, and second one, it is a fluid. Now see, the syllabus started with the general measurements, that is unit and that was a unit, the first chapter of the physics syllabus, that was units and measurement. Okay, that concludes, right, the generalized information of the entire syllabus. Now if we move on to the motion in 1D and 2D, then it was only about the kinematics, right, that deals with the motion of the particle but without cause. Then we jumped on to the NLM, the motion analysis of the motion with the cause. Okay, and here comes the work, energy and power, analysis of the motion in terms of the energy and work. Finally, till 6th chapter, we were not dealing with the configuration of the particle, we were only considering all of those things as particle. Now in 7th chapter, it jumped off to the configuration of the particle, analyzing the motion and its with its respective configuration, right? Analyzing the motion with its respective configuration. Yes or no, guys? Analyzing the motion with its respective configuration. And here comes the new part, gravitation. After that, we are going to see how the internal configuration might be having the elastic behavior, might not. Right, so this chapter is entirely about the elastic objects, right, the elastic behavior of the solids and the respective concepts and the respective laws. Are you all ready? Okay, so I think lots of discussions are going to come today, but first of all we are going to start with the very simple explanation of elastic behavior of solid. What does it states? Right, what does the elastic behavior of the solid states? I'm going to give you all a very simple example. Right, one side we are going to take rubber, second side we are going to take spring. Suppose external force is applied to rubber. Similarly, suppose external force is applied to spring. Right, what happens into the first case, right, what happens into the second case, and how we are going to compare this two. Okay, and we are going to understand this stuff, that is elastic behavior of the solids. Okay, elastic behavior of the solids. See now, whenever the external force is applied, okay, to the rubber, okay, the very least amount of the configuration, right, the change into the configuration we are going to see. Rubber will extend. Suppose if I am stretching this, right, rubber will extend for a very small length. But if we are going to elongate this spring on applying the external force, spring will be having the large number of the extension, large amount of the extension. Suppose anyhow, if this rubber is replaced by pen. Some students might be thinking, sir, this is a rubber, it is itself an elastic object, right? The beneath is a spring, it itself is an elastic object. Then how it is a, right, how it is going to be quite easy to understand. Sir, just give us the example by replacing the rubber by the pen. Suppose if this is a pen and external force is applied to it, is it possible that we are going to have the extension into it? Okay, it completely depends, right, the source that is applying the force. how and who is applying the force. If spring, manually human is applying the force, easily we are able to see the extension. But on pen, if we are applying the force, it is difficult to see the extension. Instead of that, if you are keeping this pen into the crushing machine, right, immediately it will start compressing and will get burst out. So it depends on who is applying the force, what kind of the force is applied, how it is applied. Right. Okay. This is not any kind of the technical explanation. A general explanation is going on regarding the elastic behavior of the solids. Okay. The most important term it is elastic behavior of these solids. Suppose it is replaced by pen and external force is applied to pen. If same external force is going to applied, okay, then we will be having the negligible extension. Okay, the extension would be so negligible that it is difficult to see by human eye. It is quite difficult to see right by a human eye. Okay. So, in this case, I am going to say there is no elastic behavior of the solids. In this case, I am going to say yes, the solids are showing the elastic behaviors. Wrong. This is a myth student holds while studying on this chapter. Generally, they used to avoid it. They only concentrate on the single specific right law, that is a Hooke's law. Okay, but the actual logic of this chapter lies behind. Are solids really expanding? Let's have another example of it. Right. We are having one cube. Okay. We are having one cube. Let's say all sides of the cube. Okay. Suppose this is a cube. Can I replace all sides of the cube? I had replaced all sides of the cube. Okay, this is a cube. Suppose, let us take an example. This is a room. Okay, 6 faces. Can I compare it to the cube? Yes. I have replaced all of those sides, right, by the springs. How actually, right, see, it is difficult to understand the elastic behavior of the solids through this part. Despite of, yes, they show the elastic behavior. Yes, if I'm applying the external force to the pen, it is showing the elastic behavior, right? In spite of being a negligible value, but yes, negligible is also something for physics. Okay, so it is difficult. Why I am comparing this two part in front at the beginning of this session? Because entire session we have taken the lots of examples of the springs. Lots of examples of the springs. So in this case, simply I want to tell you all, right? In this case, simply I want to tell you all that it is difficult to understand the elastic behavior by this example. It is difficult to understand this by this example. So for that reason, analogy of the spring is taken right, to understand its concept quite easily. Suppose now if I am applying external force to it, all of the springs are going to right, elongate. There will be the change in configuration of the system. But here suppose if I am going to apply the external force, right, visually you are not able to see any kind of the configuration of the system, the change into configuration of the system. But here we can easily understand how the configuration is getting changed and how the elastics are showing how the solids are showing the elastic behaviors. Right, it is really right easy to understand. Okay, now this was a very basic explanation regarding the elastic behavior of the solids. Don't get worried, lots of visualizations are going to come, but introductory part is necessary. Okay, now see, there is a difference between pressure and stress. In this chapter, we are going to deal only with the stress. Okay, both are having the same formula. The first, pressure is equal to force per unit area. Second, stress is equal to force per unit cross section area. What is the natural difference between them? If I am talking about the pressure, right, object inside the fluid, right, force is acting on the entire area. Force is acting on the entire area. Pressure. If I am talking about the stress, right, okay, if I am talking about the stress, suppose here force is applied, then stress is only developed into the cross-sectional area. We are going to understand the pressure and stress through the day-to-day life example. A very simple explanation. Some students might be having the problem of a migraine. Generally what happens, right, a small part of it stucks hard. It hits hard. Like that. So only one part is getting, so the cross section of that part is getting ache, right? But whenever in Hindi you used to say sir pakad raha hai pura, the entire headache is the best example of the pressure, and the migraine, the single nerve, right, that is itching you all and producing an ache, the best example of the stress. Analogy, there might be some limitations, but we need an example, right, analogous to this concept to understand it into the very appropriate manner, right? Now, in the elastic behavior of the solids, we are only going to deal with the stress, strains. Stress and its type, strain and its type. First, if I'm talking about stress, simply it is defined as a force acting per unit cross-sectional area. Force acting per unit cross-sectional area, right? Force acting per unit cross-sectional area, that is stress. Okay, force acting per unit cross-sectional area is stress, right? Now, how we are going to understand this stress? Very simple example. This is a cylinder, external forces acting onto it, right? The stress is developed onto the cross-sectional area. point from which we are going to face an elongation, right? Types of stress. The first type of stress that we are going to understand into the very simplified form, right? The first type, okay, that is the tensile and compressive stress. The second type of the stress, right, that is a shear stress. The third type of the stress that we are going to understand, okay, that is the thermal stress. Fourth, volumetric stress. All of those stresses are having the simple meaning, right? All of those stresses are having the quite a simple meaning. The things differs, right, is of the application. The way force is acting on the specific object, right? The way force is acting on that specific object, right? If I am going to talk you about the strain, okay, first of all we are going to discuss into the very simplified form, then in detail we will be having the discussion on the types of stress, right? After that we'll have the detailed discussion regarding the types of strains, and slowly we will move on to the Hooke's law, the stress strain curve, the applications of it, right, the combination of the rods, and first of all we are going to cover the entire theory, and at the end we are going to take out some of the best sums of it. Spring. Initially, spring is in its natural length Initially, the spring is in its natural length. Now, suppose the external force is applied to it. Suppose the external force is applied to it. Obviously, suppose the initial length is L. You are going to face, right? You are going to have the new length of this spring. And if we are comparing the initial length and the final length, obviously we are going to face some elongation into it, right? Obviously we are going to face some elongations into it. So generally the strain is defined as change in configuration by original configuration. Now, types. Longitudinal strain, thermal strain, lateral strain, volumetric strain. For the respective stresses, we are having strains. If we are having this stresses, okay, for respective stresses, we are having the strains, and for the respective stresses and strains, we are having the moduluses. Okay, we are having this moduluses, right? So it is all about the stresses and strain. Before moving on to the Hooke's law, right, okay, that we are going to understand, okay, before moving on to the Hooke's law, right, we are in the need of to understand the concept of the stresses and strain. Okay, so for that reason, first of all, let's start with the tensile and the compressive stress. Tensile and the compressive stress. Now what does it states? What does this tensile and the compressive stress states? Okay, see now it's a very simple thing that I'm going to deliver in front of you all. Right, it's a very simple thing that I'm going to deliver in front of you all. The tensile and the compressive stress. First, the force acting normally, right, force acting, right, perpendicular to the cross-sectional area that has a capability to produce the tensile and the compressive stress. So here tensile stress, it is force perpendicular per unit area. Compressive stress, perpendicular force per unit area, but this will result into the elongation into the system, while this will result into the compression of the system. One will result into an elongation, second will result into the compression of the system. Second, shear stress. To understand, see, stress is having the simple formula, force per unit area. We are going to see, right, the different applications and different ways, right, to understand the classification of it. Suppose here we are having one cube. External force is applied tangentially. Whenever the tangential force are applied to an object, it is having the capability to produce, right, the stress. See, this is an object. Suppose if I am applying tangential, right, like this way. Suppose if I am applying the tangential force like this. Okay, I'm going to give another example. Just hold on. I need to see. Yes, this is my book. Tangential, the shear stress means tangential force. Right? Tangentially, like this way. See. Tangentially, if force is applied, right, then on the specific cross-sectional area, we are going to have one stress, that is shear stress. Finally, the system is going to change like this way. Right? Okay, the system is going to change like this way. Okay, so this change phi, it is nothing else but an shear stress. It is nothing else but an shear stress. Thermal stress we are going to discuss into the later part. And if I'm talking about the volumetric stress, thermal stress we are going to discuss right separately. If object is immersed inside the fluid, so whatever amount of the stress that is acting on the from the all side, right, this is known as the volumetric stress. For this, all of those stresses, we are having the respective strains. For this, all of those stresses, we are having the respective strains. How? Simply, if I'm talking about the longitudinal strain, then for the tensile and compressive stress, let's take an example of the tensile and compressive forces, right, that are acting perpendicular to the system. Suppose this is an initially spring and is in natural length. Length is elongated, length is compressed. In both of these cases, right, strain is defined as change in the length by original length. right? Change in length by the original length, or it is another way it is defined as a delta L by L, right? Tensile and the compressive forces. Okay, change in length by the original length. Similarly, on another side, after tensile, we are having the thermal strain that we are going to discuss. Another, see, sometimes we can compare the lateral strain. Okay, the change in radius. This is also the type of strain by original radius. Delta R by R. And if I'm going to talk volumetric strain, change in volume by original volume. This is simple as it is at what we have discussed into the very rapid manner. Okay, because this thing you all are really aware of. Again, this was a one shot, so it was important to discuss into the very appropriate manner. Okay, it was important to discuss right into the very appropriate manner, because the most important thing in this chapter is all about, right, the most important, it's a very simple thing, right? Hooke's law. Up to certain proportionality limit is a part of life, right? Whatever you are doing, right? Okay, you are in foundations. Okay, you are always in foundations. Physics is only the thing that is not bounded. Okay, it is not completely bounded. Physics is only the thing. Apart from that, the entire human race on this earth, or whatever the species exist in the entire universe, are bounded by some laws, right? Bounded. I'm again highlighting this word, bounded. Similarly, if you are bounded by some XYZ laws, right? This Hooke's law is also bounded by something, and that word is up to certain proportionality limit, right? So first of all, I'm writing that stuff, right? Up to certain limit of proportionality. Up to certain limit of proportionality, right? We are bounding this thing, right? The stress produced is directly proportional to strain. The stress produced is, right, directly proportional to the strain. But kindly mark this word. This is an important thing. Up to certain proportionality, up to certain proportionality limit, the stress produced in an elastic object, it is directly proportional to, not elastic object, I must reframe that statement, right? Okay, elastic solid, the stress that is produced in elastic solids, right, is directly proportional to strain. This is what all about the Hooke's law. But up to certain limits of proportionality. Why? Question mark. As I said, physics is all about why and suppose. Why? Right? Even you can see this, right? The visualization in front. This is all about the experiment, right, of a Hooke's law. Okay, something it is loaded into an, let us take an example, a very simple example. If I'm talking about the spring, if mass m is hanged right on a spring, obviously it is going to elongate from its natural length, right? Suppose initially this was its natural length L initial, right? Now this thing, this is the final length of the spring. Obviously it is getting elongated now. So whether Hooke's law is applicable for entire process? No. Right? Is it applicable for entire process? No. If it is a perfectly elastic body, then yes, we can say, right, for entire process of stretching and getting compressed, the Hooke's law is applicable. But right now in this chapter here, we are dealing with the concepts, right, of the behaviors of solids. Not we are, see, that is a classification of perfectly elastic bodies and everything. right? Ductile and brittle and lots of stuff is there. But if we are talking about the solids, right? Okay, if we are talking about solids, then obviously we are going to face some foundations, because they are not, it is not for sure that all solids that exist into the universe, right? They are perfectly elastic. They are perfectly elastic. So that's why, right, it is written up to certain limit of proportionality. I am going to explain this thing into the detail, right, while moving on to the concepts of the stress strain curve. So don't get worried. Right now we are going on to the Hooke's law only, right, and we are going to see one of the examples of it. Suppose initially the spring is in its natural length. Initially the spring is in its natural length. Now suppose if mass is hung, right, this is A. Okay, suppose we are placing a mass on this spring, then obviously, right, okay, it will so can I say this is the initial length, or another sense, can I say this is a natural length of the spring, right? And this one is an elongated length, right? This is an L final. What is the difference of the length, right? What will be the difference of the length? The change in length, right, that will show how much amount of the strain is produced. If strain is produced, it means, right, with reference to the strain, we are always having one external force that is doing some kind of a work and producing this stress. So here mg is the force, right? Mg is the force that is applied, right, when we place that mask, right, we attach that mask with the spring, right? Mg was the force that was applied into the downward direction, right, and that force was responsible for, right, a stress, and as because of that stress is produced, obviously we are, right, observing some of the configurational changes into the body that shows a presence of strain. So it means stress is directly proportional to strain, right? More stress, high will be the configuration, more stress, high will be the configuration changes, right? More stress, high will be the configuration changes. The less stress, right, more amount of the stress, more will be the configuration changes. Less stress, less strain. Now removing this proportionality sign, what we get, right? Okay, removing this proportionality sign, right, we are getting, okay, the new constant, the constant of proportionality, that is known as Young's modulus. The constant of proportionality, that is known as what? Young's modulus, right? This is a constant of the proportionality. In another sense, right, I can define Young's modulus, or I can generally define the modulus as ratio of stress by strain, right? I can generally define, right, the modulus as the ratio of stress and strain. Modulus as the ratio of stress and strain, right? So this is what all about the Hooke's law. What actually the graph is, what actually the stress strain curve, what is an actual meaning of up to certain proportionality limit. Okay, let me give you all a hint about it, about that word, about that statement, the small, that is up to certain limits of proportionality. See, suppose M was attached, right? We saw the, right, we saw we observed the change in length into the spring. Now let's increase the mass. Suppose if 2m is attached, right, more amount of the stress will produce, more amount of the strain we are getting. Let us take an example. If we are attaching 3m, the more amount of the strain will produce, stress will produce, and that will result into the, right, getting the more amount of the values of strain. Now suppose if 10m is attached, then what, right, we are going to observe what thing, how things will go on. Is it for sure, right, that this spring is going to elongate on attaching the mass of 10m? Question mark. Now students will have, right, students will be having, right, the things into the mind. Sir, it completely depends on how spring is. Let's compare this thing to the day-to-day life. It completely depends on the nature of the human, right? It completely depends on the nature of the human, that how he is reacting to the problems. How much amount of the patience he holds. Patience. Same. It completely depends on the Y value. It completely depends on how string is, right? If I'm talking about the spring that we are, right, removing from the ball pen, it is having, it is not having that much capability even to, right, right, we can attach the 100 gram of mass with it, right? On attaching, even like on attaching the 100 gram of a mass with that spring that has been removed from the ball pen, right, it is going to get deformed. Right, so there are some certain limitations, nah, right? Now, if I'm talking about a spring that is used, right, into the bikes, in other words, the springs near sockupsers, if you have heard about, right? So those are what we can say, right? Those are like having the high value of the K, right? They can hold the high amount of the forces, right? But as compared to the spring that we removed from the ball pen, right, that is having very less value of the K. So that is a difference that I want to, right, show you all in front. There is a difference. So whether this string is capable to hold the 10m mass or not, it completely depends on the nature of the spring, how spring is, and up to what limit he is able to produce the stress, up to what limit he can change its configuration. Two most important terms, right? What will be the capability, right? Up to what limit, right, the string is capable to hold the mass, up to what limit the string is, sorry, string not spring, the spring is capable to produce a strain, and up to what limit the spring is capable to give the values of strains. Before that, what will happen? After that proportionality limit, what will happen, right? That we are going to see into the graphs, right? So this is all, right, about the Hooke's law. Okay. So removing this proportionality sign, we are getting Young's modulus, right? And this Young's modulus is a ratio of the stress by strain, right? If it is the volumetric stress produced with respect to the volumetric strain, then we are having bulk modulus, right? In bulk modulus, we are also having the two classifications, right? Bulk modulus, right, for adiabatic process and for isostatic. That thing we are going to see into the thermodynamics, right? So what kind of stress is produced? Ratio of what kind of a stress that is produced to its relevant strains will give, right, the new constant of the proportionality. If it is a tensile or compressive, then we are saying it is a Young's modulus. If it is a volumetric stress, right, okay, and if it is a volumetric stress and with respect to this it is a strain, then obviously we are naming it as a bulk modulus. So lots of things are there. So this is what the basic idea of the Hooke's law is, right? Okay, now while conducting an this experiment was conducted, right, okay, this experiment was conducted to right, to determine the, right, experimental value of that constant of proportionality that is obtained from the equation. For that, one graph was plotted. That graph was stress versus strain graph, right? So if I'm talking about a graph that is stress versus strain graph, right? Stress versus strain. This graph will help us, right, in determining the constant of proportionality, that is Young's modulus. Suppose if we are conducting an experiment, this is the value of the stress and this is the value of strain. For Hooke's law, as the stress is directly proportional to strain, it means when we are conducting an experiment, we are getting its relevant observation, right? This graph should be straight line. In limits of proportionality, this graph should compulsory be the straight line. I use that word into the Hooke's law, na? Up to certain limit. Up to certain limit of proportionality. Up to certain limits of proportionality, this graph, right? I'm talking about that range, I'm talking about that limit up to which the Hooke's law is valid. Within that range, this graph should be compulsory straight line. I am talking about, yes, again I'm repeating that statement. I am talking about the range, a limit up to which the Hooke's law is valid, right? Okay, up to that limit, this graph should be straight line. Before and after, what actually it is, we are going to discuss in detail, right, in the concepts of stress strain curve, right? But right now it should be the straight line and the slope is a Young modulus. Slope, it is the value of the Young's modulus, that is stress by strain. You can see in this visualization, right? Mass is hanged, spring is getting elongated, then up to certain proportionality limit. See, suppose, let's plot this graph in this visualization. Suppose the weight is 10 Newton. For that, we are having the respective elongation. Suppose if we are increasing a weight to 40 Newton, so with respect to this, we are having an elongation. So this will be my first point, right? And this will be my, right, second point. Suppose if I'm increasing a weight, right, to 80 Newton. So for that, we are getting the respective elongation, right? So up to that limit. Now see, 80 Newton is the limit of a spring. Up to 80 Newton you can attach a mass, and after that it will get, whether it will get deformed or it will get loses elasticity, right? We are not aware of what is going to happen, but we are only aware of our foundations, right? That limit of proportionality, that is 80 Newton. Up to 80 Newton we are having the graph like this way, right? After that, what will be the nature of the graph, right? We are not aware of. So that's the up to certain limits of proportionality. Okay, so the slope of stress versus strain graph, right, always gives its modulus, always gives its constant of proportionality. Okay, now let's move on to the stress strain curve, and to understand the stress strain curve we need to take one example, right? Okay, by showing that we are going to understand that stuff into the convenient manner. Now let's have an example in front. See, I'm taking one spring. Right, see, one rigid wall is there, right? I'm having a spring of spring constant K. Initially no force is applied, right? Initially no force is applied. Can I say here, right, no force is applied, right? No force is applied, right? If no force is applied, it means it is a very simple thing, right? We are not going to see any kind of an elongation or compression. right? So can I say no elongation, no compression, right? No elongation, no compression, no force is applied, right, in first case. Now suppose let us take an example, right? If we are applying the F amount of the force, obviously the spring will get elongated from its natural length, right? Spring, okay, just a minimal amount of the force, right, we are applying, then spring is getting elongated from its original length, right? So we are facing an elongation, okay, great. So while plotting the stress strain curve, right, initially, right, while plotting the stress strain curve, initially everything was at 0, right? Now I increase the value of the, right, forces F, right? Then we got a relevant strain to that. So the graph is like straight line, right? Now I am increasing the value of F, right? Again, increasing the value of F, then we are having the more elongation. Suppose this is a new value of a strain, that is its limit, and this is a new value of F dash, right? This is a limit up to which, right, I can apply the F, right? It doesn't mean that external force is bounded, that then he can or it can only apply the value of F dash. No. Even you can apply your even you can apply your 1000 Newton, right, whatever you want. But there are some limitations of this spring. The spring can hold only up to the value of F, and that it's a limit of proportionality. Up to the maximum limit of F dash, this spring can elongate, and it has tendency to come back to its original position. It has tendency to come back to its original position. It has tendency to come back to its original position. Source is rigid, right? It is rigid in nature. Now he applied the 4 times F dash value or 8 times F value, whatever. It will be the large amount of the F. Beyond this, the spring will lose its elasticity. Beyond this, the spring will lose its elasticity, right? Beyond this, spring will lose its elasticity. Suppose if more than, right, if we are applying the value of the force that is more than F dash, right, the spring will lose its tendency to come back to its original position, right? Now we are crossing the limits of proportionality. You can see this example, right? This was the section, this was our limit of proportionality. Up to this, Hooke's law holds valid. And we are getting the graph as a straight line. Beyond this, first step, object will lose its elasticity. Second step, if still we are applying the force, right, after the object has already lost its elasticity, then occurs the deformation, right? If I'm talking about a simple spring, let us take an example. I'm having one spring in my hand, I'm showing you all in front. So you can see the spring, right? This spring, right? If I'm trying to apply a force, right, the spring will face an elongation, but up to certain limit, right? Up to that limit, right? The force is applied up to certain one specific limit, right? If the force is applied, the spring has tendency so that it can come back to its original position, but beyond that, spring loses its elasticity. So beyond that, if spring loses its elasticity, it means we are crossing the limits of proportionality and Hooke's law fails. Within the limits of the proportionality, the spring has tendency to come back to its original position. Hooke's law is valid, everything is fine. The graph is a straight line. Now, this is the fourth step. Beyond this, the spring has lost its elasticity. Again, now, right, okay, we are applying the value of the force, and that is value is like quite high. And there occurs the fracture point. Okay, these things are only important, right? Beyond this, right, lots of things you can see, like ultimate strength and yield and everything, right? Ultimate strength is a point, right, between the object when it's it is right. The ultimate strength is in between, right? The point in between the fracture point and a point where the spring loses its elasticity, right? Okay, lots of things, right? Into the thousands of resources, it is explained into the different way, but right, in the entire topic, this thing is only this much amount of the things, right, are only important, right? Okay, up to, so this is what all about, na? I told you all, na, this one, up to certain limits of proportionality. That limit of proportionality is for an elastic object, right? Right, we are having this boundation. For an elastic object, we are having this boundation. What kind of a boundation? Up to limit. Up to what limit? Up to the limit, right? Okay, till this object will have a tendency to come back to its original position, else things will go weird. Hooke's law fails. So this is all about the stress strain curve in final, right? If the source is not stopping, right? Okay, if this force applied value will not become less, right, or whatever it should be, right, the object will get fractured. So whenever we are dealing with the elongation and the compression into the spring, right, see, let us take an example. If this is a spring, on application of the F force, right, the spring is getting elongated. On application of, right, X force, right, the spring is getting elongated, right? And for this elongation of the spring, right, up to certain proportionality limits, right, one restoring force is generated, that is Kx. This restoring force, what actually it do, right, it will help, right, an object to regain its original position on removal of this external force. Right, so see, whenever an external force is applied, right, work is done. Now this work is done, obviously it is against the restoring force. We are applying the force, we are facing an elongation, right? Obviously the work is done, and whatever the amount of the work is done, right, somewhere the Kx, the restoring force, is involved. For this, right, Kx, the restoring force, this is a conservative force, right? This restoring force, it is the conservative force, and whatever, right, the work is done for the conservative forces, it is always stored into the form of the potential energy. If mg does the work, it is stored into the form of the gravitational potential energy. If Kx is doing the work, right, or it is against, right, whatever it should be, it is stored into the form of the elastic potential energy. So here, whatever the work is done, it is stored into the form of the elastic potential energy, right? And you have seen the derivation, right, relevant to it and that is u is equal to half kx square, right? And we got this derivation by dw is equal to f dot dx, replacing the value of the x as minus kx dx like that way, right? We are getting the potential, the elastic potential energy, right? Whenever the spring is facing an elongation or compression, there is always an energy stored inside it, and we are naming that energy as the elastic potential energy, and its relevant equation is this. Obviously it is a scalar form. Apart from this, if I'm talking about a three-dimensional object or any elastic object, we are sure that if work is done, energy is stored. But what amount of the energy that is stored per unit volume of an entire object, right? What amount of the energy that is stored per unit volume, that shows the example of the energy density, right? That is equal to half stress into strain, right? Okay, and that energy density is energy, right, per unit volume. Lots of formulas are there, right? You can make it out replacing the Hooke's law, right? You can make out, see, suppose if I'm talking about a Hooke's law, right? See what we got, the stress is directly proportional to strain. Okay, so sigma, that is equal to y strain, sigma, that is equal to force per unit area, stress, that is y delta L by L, that is the relevant strain. So value of the y is FL by A delta L, right? If you are replacing this Hooke's law, right, if you are replacing this Hooke's law, right, into the relevant equations, right, then we are getting the new outputs. If we are replacing the Hooke's law into the equation of the energy density, then we are getting the new outputs, right? Okay, it doesn't mean we are going to change our base. The base is that energy density, it means energy per unit volume, and we can define it by the respective formula, right? Now lots of formulas that, as you all are aware of, right? Now there is a relation between the spring constant and the Young's modulus, and that will help us, right, to understand the concepts when the springs are connected in series, how to determine the equivalent K, and when the springs are connected in the parallel, how to determine the value of the K. So first of all, we are going to see the actual relation between the spring constant and the Young's modulus, and then we are going to see some of the cases of the combinations of the rods when they are considered as the springs. So spring constant and the Young's modulus. See, suppose if, right, F is applied to an object, then we are having the value of the restoring force, right? So according to the Hooke's law, can I say force that is acting per unit area, that is equal to Young's modulus delta L by L? Can I replace this value of the force as K delta L, and that is the restoring force is Y delta L by L? Delta L will get cancelled. We are getting the constant of proportionality is YA by L. That is an actual relation of a spring constant, right, and Young's modulus. That is an actual relation of this spring constant and the Young's modulus. And this relation we are going to use, right, in determining, right, the new results, right, when springs are connected in series and they are connected in parallel, right? When springs are connected in series and they are connected in parallel. Combination of rods. Combination of rods. See, this kind of the sums, right? Okay, they are already asked in an examination, right? Okay, the sums based on this concept, right? Okay, I'm going to show you some PYQs also based on it, right? But first of all, let's move on to the actual, right, concept, right? Okay, let's see this thing from the ground zero. What will happen, right? Let us take an example. This is one rod. This is the second rod. This is a rod made up of the steel material, and this is a rod made up of the brass material. If weight is attached to it. So my question to you all is whether we are going to face the elongation or compression in it or not. Obviously, we are going to face some compression or elongation in it. Yes. But how to solve this kind of the sums? Let us take another example. Suppose if two rods are attached like this way. The first one is steel. The second one is brass. And mass attaches to it. On attaching the mass, whether this rods will face or elongation or not. Right? Whether they will, whether we are able to observe the elongation in the objects and the solids or not. To solve this kind of the concepts, always keep one thing into your mind. That is, always see, we are saying the elastic behavior of the solids now, right? Then it is wrong to consider this solid as an individual spring. We can consider it because we are understanding the elastic behavior of the solids. To understand it into the appropriate manner, yes, we can consider that part as a spring, right? So always consider, this is only the way to understand these sums. Always consider, right, the rods as springs. This is the best analogy, right, to understand this concept. Best analogy to understand this concept. Right? Now, how the things will appear in front of me? Right? How things will appear? First case. This is a spring that is made of some material. Right? This is another spring that is made of some material. But I can't say it is having some Young's modulus. But yes, I can say this spring is of the spring constant K1 and this spring is of the spring constant K2. I can't say it is made up of this material, but yes, I can determine the value of I can give the value of the K. Even I can correlate the value of the spring constant with its respective modulus. Right? So we can, right, with that value, we are able to identify of what material this spring is made. Right? So this is an indirect explanation to understand this concept. Right? If rod is there, we can consider it as an spring. Right? This is an analogy to understand this concept well. Second, if they are connected in series, it's okay. No worries. This is a spring of spring constant K1. This is a spring of spring constant K2. Right? Right. So there might be, if these two things are connected, right? So there might be some effective spring constant that will produce the same result as these two springs are giving. Here also we are having the value of some effective constant and it is giving the same result as these two springs are giving. That thing, this would be our next step to determine the formula of this K effective, right? And to compare it with the concepts of the Young's modulus, as this solids are elastic. They are showing an elastic behavior, right? So first of all, I'm sorry, I am extremely sorry for that, right? Okay, yes. If springs or rods are connected in series, springs or rods, suppose this is a rod, right, that is having Young's modulus y1, This is a rod having Young's modulus Y2. Mass M is attached. Can I compare this analogy to the springs? Right. This is the first spring that is having spring constant K1. This is a second spring. Right. Mass is M is attached and this is a constant K2. Now as they are in series, right? Okay. The elongation into the first will be delta L1 and elongation into the second will be the delta L2. So what will be the resultant elongation? That is delta L is equal to delta L1 plus delta L2. In springs, right, elongations of the springs, right, those who are connected in series are different. The force applied on them is same, right? The elongations are different. So in this case, what we are going to get? Can I say according to the Hooke's law? Right? Force per unit area stress is equal to Y delta L by L. Can I say delta L that is equal to FL by AY? Right? So if I'm talking about the resultant, can I replace this equation and can I consider this is equation number 1? Yes. Can I consider this is equation number 2? Replacing 2 in 1. Replacing 2 in 1. So what I will get? F into L equivalent whole divided by area into Y equivalent, that is F into L1 whole divided by, right, area into Y1 plus F L2 whole divided by area Y2. It's A equivalent A1 and A2. This is the general formula. Now suppose area of the cross sections of both are equal. If A1 is equivalent to A2, right, and even F is constant in both, then finally we can write this equation as L equivalent by Y equivalent, right, that is equivalent to L1, right, this one, L1 by this one, L1 by Y1 plus L2 by Y2. Suppose if we are keeping the value of the F as like this way, right? Now if F is getting cancelled, then we are getting the, right, equivalent, Y equivalent, right? We are getting this Y equivalent, right? Now suppose if we are replacing the value of Ka, right, K as Ya by L, right, in this equation, right? So finally we are getting the K equivalent as K1 K2 whole divided by K1 plus K2 when springs are connected in series, right? So this is how the things are resolved, right? Okay, this is how the things are resolved, right? Can I replace Y as Ka by L? Yes, Ka by L. Obviously the area is going to same, the things will get cancelled out, right, and we are getting the final equation as this way. Now suppose if strings are in parallel, we are not moving on to the right derivations of it, but we are having the final equation. If strings are in parallel, this is the value of the K equivalent or K effective, right, because in parallel, right, force are getting divided, right, force are getting divided always, right? Okay, so this is a new concept, right? Sums based on this are already asked into the NEET 2019 and 20 paper. We are going to see that stuff also, right? Okay, and the final part, this is a thermal stress, right? This thermal stress obviously we are going to see into the, right, heat transfer also, but I'm going to show you all. Suppose these are the two rigid rods, two rigid walls, right, and in between the two rigid walls obviously one rod is connected. Between the two rigid walls, one rod is connected and continuously heat is supplied to it. On application of the heat, see, you can see into the visualization, when heat is applied to the fine ceramics, right, obviously it is, we are observing the change in length of it. So thermal stress is what? stress as of a simple term, thermal energy. Stress as of the thermal energy, right? Again, if we are defining it as a stress is equal to Young's modulus of strain, that is delta L by L, right? Okay, now consider this is equation number 1. According to the concept of expansions in solids that we are going to see into the next chapter, right? We can use this equation, and if I am replacing this value, I am getting the thermal stress as Y alpha delta T, right? Stress is because of a mechanical force, we are defining it as a tensile compressive. Stress as because of any kind of the thermal energy, right? Okay, then we are defining it as a thermal stress. It's a very simple thing, right? Don't worry, we are going to see that stuff into the heat transfer also, because at this position of the time you are not aware of how this equation we are getting, right? How with the expansions, right? Lots of things are there, right? Lots of ways are there, right, through which the solids will get expand, right? Okay, now let's see some sums related to the Hooke's law, right? Okay, now the stress strain curve drawn for the two materials. We are drawing the stress strain curve for the two materials. This is for the material X, right? And this is for the material Y. This question is asked into the Odisha NEET 2019, right? It is observed that ultimate strength point and the fracture point are close to each other. Ultimate strength point, it means this is an ultimate strength point and this is a fracture point. We have seen this stuff into the stress strain curve. Ultimate strength point, USP. This is the fracture point. For X, it is nearer. For material X, but far apart for material Y. For material Y, this is a fracture point and this is an ultimate strength point. For X, they are nearer. For Y, they are far. What kind of the object it is, right? What kind of an object it is? It's a very simple thing. The first one is a brittle and second one is a ductile. The distance between, right, if the USP and the fracture point, the ultimate strength point and the fracture point are quite nearer, it means on application of an force that object is easily breakable. It means it is brittle. If these are far away from each other, then obviously it shows the ductile behavior. So X is brittle, Y is ductile. See, based on this stress strain curve, the question is asked into the Odisha NEET 2019. See, Karnataka NEET 2013, right? We saw this sum, right? The combinations of rods, right? Let's see this. If the ratios of the diameters, lengths and Young's modulus of the steel and copper wires are shown into the figure. See, ratios of diameters, lengths and Young's modulus are P, Q and S. Diameter D1, D2. Ratios of the diameters, right, are P. Lengths and Young's modulus L1 by L2, that is ratio is Q and Young's modulus ratio is S, PQ and S. Then corresponding ratio of their increase in the length would be what? Corresponding ratio of increase in length, delta L1 by delta L2. According to the Hooke's law, right, I'm writing this term according to Hooke's law. Can I say force per unit area, that is equal to Y delta L by L? So delta L, that is equal to FL by AY. Right? Can I use this equation? Yes, I can use this equation. Can I consider steel as number 1? Can I consider copper as number 2? For copper, the force is only 5 mg, but for steel, the two blocks are attached. It is 5 mg plus 2 mg, it is 7 mg. For copper, this 5m is only applying a load, but for steel, right, 5m and 2m both are applying the load. So can I say for steel, delta L1 that is equal to, sorry, seven mg into L1 by area can we replace it as a pi d square by 4, right? Can we replace the area of the cross section as the pi d square by 4? Yes. It is into 4 by pi d1 square into Young's modulus of y1. For copper, we are having delta 2 Se. It's 2m and it is 5m, right? So for copper, we are having the 5 mg, right? So it is 5 mg, right? Okay, into this is L2 into 4 by pi d2 square, right, into y2. Can I take the ratio of 1 by 2? Corresponding ratio of increase in their length would be, right? Okay, then we are having, right, delta L1 by delta L2, taking ratio of this two equation, right? I think it will be 7 L1, right, by d1 square y1 and into 5 L2 into d2 square by y2. So delta L1 by delta L2, that would be 7 by 5 L1 by L2 y2 by y1 d2 square by d1 square, right? So delta L1 by delta L2, 7 by 5. L1 by L2 is Q, 7 by 5 of Q. Y1 by Y2 is S, so it is divided by S, P square. So this will be our answer, 7Q by 5 P square S, right? 7Q by 5 P square. This, right? So this is how, in this also, right, the combination of rods are asked, right? Okay, the things are there, right? And these are also helpful from the JEE point of view. A wire of length L and the area of cross section. See, this question is asked, it's a very simple question using the Hooke's law. It is asked in NEET 2020. A wire of length L, area of cross section A is hanging from a fixed support. Wire of length L, length is L, area of cross section is A, is hanging from the fixed support. The length of the wire changes to L1 when M is suspended with its free end. Suppose if M is suspended, right, the new length we are getting as L1. The expression of the Young's modulus is very simple. Hooke's law. According to Hooke's law, right, according to the Hooke's law, right, Y delta L by L is equal to force per unit area, right? Okay, so can I say it as what? Force is mg, right? Force acting is mg, right? What we need to calculate? We need to calculate the Young's modulus. So Y is equal to FL by A delta L. F, that is mg L. This is an original length, this is area. What will be is change in length. Initially the length was L, the final length is L1. Then obviously the change in length we are going to get L1 minus L. Replacing it here, finally we are getting it as mgl whole divided by area L1 minus L. Right? The fourth is the perfect answer for this specific question. When a block of mass m is suspended, see this question is asked in NEET 2019. When the block of mass m is suspended by a long wire of length L, the length of the wire becomes L plus L. The new length becomes C. Initial length, that is equal to L. Final length, it becomes L plus, right, L. Okay, sorry, initial length is capital L. So what will be the change in length? Del. From this equation we can define it as N L. What is an elastic potential energy stored into the spring? Right. So what is the formula of elastic potential energy? Right. Elastic potential energy. Lots of formulas are there. Right. Lots of formulas, right, are there. So can I say it as a half, that is stress into strain? Can I say it as a half kx square? It's prior to use this formula. It is half kx square, that is half force into x, right? And finally we are getting it as a, right, the elastic potential energy as a half, force is mg, right, and we are having it as a L. So the elastic potential energy stored, that is mg L by 2. So students, it was all about the solids, and now next lecture is going to come upon into the fluids. So guys, this is Indrajit Singh, right, signing off from the desk. Bye bye, Sat Sri Akal and Namaste from my side, Bachaji. Bye everyone. Stay at home, stay safe, stay healthy amidst this pandemic. I will be waiting for all of your comments beneath the video. Bye Bachaji.